Grading ring. We have the insulator supporting high voltage conductor. Insulator is installed on the grounded surface, and it turns out that potential distribution along the insulator is not linear. The supporting insulator head is overstressed, while the electric field strength at the bottom of the insulator is comparatively low. Grading ring is used to affect the potential distribution and make it more linear along the insulator. Electric permittivity of the insulator is 2, relative electric permittivity of the air is 1, high voltage potential is 110 kilovolts multiplied by square root of 2 divided by the square root of 3. The geometry features rotational symmetry, and we will simulate it in two-dimensional electrostatics. Our task is to find the optimal ring position that gives minimum deviation from the linear distribution of the electric potential along the insulator. Okay, let's start QuickField now. In QuickField I create new problem. Problem name is insulator. Next. Problem type is electrostatics, model class is axisymmetric, length units are meters. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. Open, and here you can see the geometry model imported. In QuickField the axis of the rotational is a horizontal one, and we should rotate the model by 90 degrees. Edit, select all, edit, move selection, rotation, minus 90, rotate in clockwise direction. In axisymmetric model, all objects should be located above the axis of the rotational. Well, indeed, that is a symmetrical problem. No need to draw more than it is required. So I switch to insert mode, choose the line type to be the straight line, click and draw the horizontal line along the axis. OK. Now I will switch to the select objects mode, select all objects below the axis and delete them. Right click, delete selection. Yes. Here you can recognize the insulator and the high voltage conductor cap. Let's assign labels. Through labels we will specify physical properties. Switch to select objects mode, click the object to select and type in the label name here. This is the insulator, and for the insulator I specify relative electric permittivity, which is 2. OK. Click here. This is air. For the air, relative electric permittivity is 1, and there is no electric field inside conductors, so I do not assign label to the conductor. Instead I will assign label to the conductor surface. Click to select and hold the Ctrl button pressed to select multiple objects at the same time. All these edges belong to the high voltage conductor. So for these edges I assign label high voltage. And for this label I specify electric potential, which is 110 kilovolts times square root of 2 to get peak value divided by the square root of 3. You see, for some parameters QuickField supports not only values but the equations, and these equations could be a function of coordinates. Okay. In fact, the electric field is distributed not only in the insulator but also in the air outside, so we need to add the air to the geometry model. Zoom out, switch to the insert objects mode, change the line type to be the straight line, click and drag, then release, and I will draw the line here along the axis. Now change the line type to be the quarter arc and draw the arc. Switch to the select objects mode. This would be the air, and these edges belong to the grounded surface. Grounded. For these edges I specify 0 electric potential. Okay. QuickField automatically sets proper boundary condition at the axis of the rotation, and I'll let QuickField to use default boundary condition at the outer boundary. The geometry model and data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be constructed. Now save all problem files and run the analysis. Problem has been solved. Let's take a look at the results. Here you can see the electric potential lines. You can adjust the picture and switch on the color map of the electric field strength. Indeed, at the top of the insulator, the electric field strength is higher than at the bottom. The correspondence between the colors in the numbers you can see in the legend. To get exact value of the field parameters, you can use the local values tool. Click any point and you get electric potential value, electric field strength value, and other parameters. You can edit the point coordinates. You can also use the contour tool to construct XY plot. I am interested in the electric field potential distribution along the insulator surface. So I switch on the contour tool. Let's zoom in. Click edges one by one to construct the contour. Okay, I have constructed the contour along the insulator surface. I'd better save the contour in a file. File, save status, insulator surface, save. Now let's take a look at the XY plot. Here is the electric field strength distribution, and this is the electric potential distribution. Indeed, the potential distribution is highly nonlinear and the electric field strength is high. Let's switch to the table. Set the tabulating step to be 1 centimeter, 0.01 meter. Okay. And I need only the distance, the electric potential and the electric field strength. Okay. Now let's copy all these data, edit, select all, edit, copy to the Microsoft Excel document. Paste. And I will construct the XY plot here. I better use the secondary axis for the electric field strength. On the right is the electric field strength, on the left is the electric potential. Let's add the grading ring to the geometry model. Here is the picture from the Wikipedia. This is the insulator and this is the grading ring. The ring is located some distance from the top, and the ring diameter is about 3 times the insulator diameter. And the ring has the same potential as the high voltage conductor. Open the geometry model. Let's zoom in, remove the mesh, switch to insert mode, change the line type to be the half arc, and draw the circle. This is the ring cross section. And remember, this is a axisymmetrical problem. Horizontal axis is the axis of the rotational, and this is the ring radius. Ring is made of conductor and there is no electric field inside the ring, so I will assign label only to the ring surface. Select everything, but assign label only to the edges. The edge has the same potential as the high voltage conductor, so I will choose this label. Now if I click high voltage, I can see which edge has the high voltage potential. Okay, let's build the fine element mesh, save all simulation files and run the analysis. Let's take a look at the results. I will restore the contour file, restore status. This is the contour. Open the table, adjust the tabulating step 1 cm, adjust which columns to display, distance, electric potential, electric field strength. Select all data, copy data to the Excel file and paste it here. Let's add new data to the chart. Okay. And the potential I would like to display on the primary axis. Here you can see the difference. The blue line corresponds to the electric potential distribution along the insulator surface without the grading ring, and the gray line corresponds to the potential distribution along the insulator surface with grading ring. Without the grading ring, the electric field stress is 1.3 kilovolts per millimeter, and with the help of the grading ring, the electric field strength was reduced to 0.6 kilovolts per millimeter. Ideally, we would like to get the linear dependency of the electric potential, but that is not possible with only one ring. But now it is fast and easy to adjust the ring position, run the analysis again, and within few seconds get new results. This way you can find the optimal position of the ring. If you search our website for the grading ring, you can find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures and download the simulation files. Simulation files may be opened and viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.